You have chapter 6 for me, yes? Please. Thank you. When I am dealing with a normal distribution whose mean and standard deviation are known, I'm going to write n mu sigma just like that. And most of the time, once I know the mean and standard deviation, I can write up that formula that I showed you in the textbook that I promised you we were rarely, if ever, going to use. I hate that formula. And it gets worse because every different mean and standard deviation causes me a new function, causes me a different set of issues in dealing with that. But let's consider what happens if I just use a mean of 0, the standard deviation of 1. Well, to me, one of the best parts about this is that that's actually the picture I've been showing you of the normal distribution this whole time. That function is this one. That's centered at 0. And its standard deviation has width 1. That's exactly the picture I want to use when I'm using this particular standard deviation and mean. I like this one so much, I'm going to call it the standard normal distribution. And if you really want, I can give you the formula, but I'm never going to use it. You don't have to write that down. That's completely arbitrary at this point. But let's suppose for a moment that I am using a function for a population of people. Male height. The average height of an American male is 70 inches, 5'10". The standard deviation is 2 inches. So I can think about that. But if I drew the picture of that, it would look just like this. I just have to change the labels on the x-axis and on the y-axis to make it the correct picture. The standard distribution looks exactly the same as that one, except moved over and stretched a little. I can do that with a pinch zoom, man. That's easy. But we already did a transformation to our data previously. Back when we were talking about descriptive statistics, we talked away about transforming our values, our data, to a standardized version. So if I had a bunch of X values, I could standardize them. What letter did we use for standardized data? Aha! Hang on a second. Consider values from this population. I measure someone's height. Let's say this person is 6 foot tall. They are 72 inches tall. Their z-score tells me where they are in the distribution, right? It tells me how many standard deviations above the average they are. In the normal distribution at 70, '72 would be one standard deviation over, right? What's the z-score for 72? Yeah.
Would it be 72 minus mu over 1? So do we know mu, or do we have to solve for mu?
Well, I have mu. Mu is right there.
72 minus 70 over 2, so that looks like that would be this. In that case, it's 1.
Which means if I go to the normal distribution N01, I'm at that spot, aren't I? The only difference between these two pictures is the labeling.
This might be a stupid question.
The only stupid question is, do I need to keep breathing? And if you ask it, the answer is no.
Why is there standard deviation 2 in the formula?
Well, because I actually over here said that the population of human being males, American males, has an average height of 70 inches and a standard deviation of 2 inches. I got that from my data. I started with that. But knowing that means I can take any normal distribution I want, no matter what the mean is, no matter what the standard deviation is, and shift it to use this one. By transforming from X to Z, I can convert any distribution to the standard one. Now, since we're thinking about probabilities as areas under curves, instead of having to find areas under different normal distributions, depending on the mean and standard deviation, I can just find areas under one normal distribution. This one, the standard. Now, I am the first person to tell you that finding this areas under here, is going to suck. So somebody already did it for me. And I can write a piece of computer code that'll do it for me too. And somebody already did that. In all the places I'm going to look, they've already done it for me. So let's think about this. There are two different versions of the normal area table in the back of the book. But I need to remember two things. First thing I need to remember is that this picture is symmetric. It's the same on the right and the left. And all of these numbers here represent z-scores. So if I wanted to know, we said this person is 6 foot tall, their z-score is 1. What is the chance that when I pick a random American male out of a population, their height will be between 70 and 72 inches? Remember, that's our average. That's where we have this person. I would need to figure out the area between 70 and 72 in this picture, right? That's not easy. But if I transform here, then these x's become z's. What's the z-value over there on the right for 72? We worked that out. That's 1. What's the z-value for 70? Sorry, somebody said it. 0. Because the top is going to be 70 minus 70. So really, this area in this picture is this area in this picture. This is in your book. Appendix C in your textbook. I didn't make this up. I didn't print this out of some crazy. This is in your book. But now I have to find the z-score of 0 and the z-score of 1. And in this picture, look at what is shaded. What is shaded is from 0 to the z-score I want. Which means if I want to know the answer to the question I just asked you, I need to find z equals 1 on this table. This table is laid out so that the first decimal place is down this column, and the second decimal place is across. So if I want 1.00, 1.00 is here. The chance that I pick a random American male and their height is between 70 and 72 inches is 0.3413. And this chance is exactly the same this transformation works completely for me. Allows me, instead of having to do stuff in any distribution, to use the same distribution over and over. So I don't care whether we're talking about the height of a human male, American male, or the petal length on a daffodil, or the height of a stalk of corn. These are all normally distributed objects. And I can ask probability questions about normally distributed populations using one normal distribution every time. The big important part here is to make sure I'm dealing with z-scores. Questions? Yes, sir.
Can you please show us again how did you get 0.3413?
Absolutely. Out of my table, since I'm looking between 0 and 1, I'm going to find 1. 1.0 for a z-score. 1.0 what? Well, 1.00 is this number. If it was 1.05, I'd go to this number.
Okay, because if it wasn't like 70 to 0, we would have done like the subtraction.
Right. Well, if it was 70 to, yeah, that's you're right ahead of me exactly where I want to be. So if I ask the next question, what is the chance that a person is taller than 72 inches? Right? Well, that would be the same as asking what is the chance that their z-score is bigger than or equal to 1. Now think about the picture we were just looking at. In this case, I'm asking about this area, aren't I? And we just found out that this area is 0.3413. That whole side of the picture, how much area is on that whole side?
And 0.5.
Because the whole thing is 1, right? And it's symmetric, so half of it is on the right and half of it is on the left. The whole side is 0.5. So if I want this, I'm going to take 0.5 minus 0.3413. Now, what is that number? You all have calculators. You don't have to do this in your head.
0.1586.
Did you not use 3 here? If I do 3413, I should get 1587. We're using.
I didn't round the last.
Okay.
One, that's all.
Yeah, which means you looked it up in a different way rather than using my table, right? I did say I could do this in a bunch of different ways.
Yeah, I used I did CDF, normal CDF.
Okay. The normal CDF. The CDF measures all the way from the left as opposed to measuring from 0. Think about a CDF. A CDF, cumulative, means I have to start all the way on the left, not from the middle of our function, right? And that is also available to me. That's measuring from the middle. This table is measuring from the left end. Notice this table starts with z values that are negative because we're measuring from the left goes to minuses, right? So if I wanted to go to z equals 1 on this table, I'm not going to get 0.3413. Alessandro, here's a different section. If I look for 1.0 in this table, it's not even on the first page because all of these z values are negative. I have to go to the second page to find 1.00, and I get 0.8413. Right?
I got the right answer.
You got 0.3413?
Mm-hmm.
Using
Normal CDF, yeah. Using a range of 70 to 72.
Okay, hang on. That means you did a different process altogether.
Okay.
Hold that thought. You didn't do a transformation. You left it in X as opposed to transforming the Z at all. On my calculator, I have a normal distribution, right? And if I want a normal CDF, it asks you, where are you going from and to? With my table, I was going from 0 to 1 with a mean of 0 and a mean of 1, right? And if I do that, I get 3413. That's table 1. But the CDF really should start all the way on the left, and that's why in that distribution, when I first looked, wrong button. When I first looked at it, it showed this, right? What does negative 1 E99 mean?
Would it be like -1 raised to 99?
Almost. It's -1 times 10 raised to the negative 99. That's minus infinity, right? That's negative huge. So we're starting all the way on the left. If you tell that to be 0, then you'll make the numbers in table C1. And then, yes, you'll get this value. And then when you do 0.5 minus this value, you 0.5 minus this value, you get 1586. I'm not going to care about that last digit being different. If this only goes to 4 decimal places or 5 at most, if you're off in that last, but I'm going to assume a round off of some type.
Is there anything like wrong with not transforming it?
No,
Okay.
no. But the reason for doing the transformation is because I will do a lot more with z-scores than I will with x values because of the z-score can apply to any population. This doesn't even tell me what I'm asking about, right? It just gives me z-scores and says start here. So let's take a crack at number 17. Now, the reason I'm going to do this without any technology first is because I want to draw the pictures. People, I don't care whether you're going to do this on your calculator in Excel or using the table. I want you to see the picture of the normal distribution and draw on it so that we can figure out where we're starting and ending. So in problem 17, it says we're going to go from negative 1.22 to 2.15. Even a crappy picture is worthwhile. I can never draw a normal distribution properly to save my ass. But negative 1.22 is going to be over here somewhere. And 2.15 is going to be much further over on this side. And what I want is this area. You have at least two different ways without any technology to decide how to get this. And it's going to depend on which way you want to do it. If you want to jump directly to the calculator and put in the lower and the upper and be done in one swell swoop, that's great. I'm going to push this a little differently. I see two different pieces, right? Then I can use table 1 that starts in the middle. And I can think about this as two pieces. The left piece and the right piece. Now in my table, C1, the picture at the top of C1 looks like this. So it measures from the middle to the right. This part is correct. This part's on the wrong side. But that graph is symmetric. And that means that the area on the left is exactly the same as the area on the right. So I can flip this to the other side. I can say this is going to be positive 1.22. And positive 2.15. And I'm adding those. Then I can go to my table and I can get both of those numbers. 1.22, based on my table, C1, 1.1, 1.2, 0, 1, there's 1.22, 3,888. $2.15, 2.1, 0, 1, 2, 3, 4, 5 is 4,842. And when I add those together, I get my total chance, 0.8730. And that's not the only way I could have solved this problem. But again, I'm going to start with the picture. This picture, I can also think of in the C2 table. The picture in C2, oh boy, that's a really crappy picture. The picture in C2 starts at the left end, right? So I could think of this picture as taking this whole thing and then taking away this bit. Doesn't that give me the same area? If I take the whole thing from 2.15 all the way to the left, and then I take from 1.22 to the left and subtract it off, that'd give me the same piece. So I could do, let me write it this way, z less than or equal to 2.15 minus less than or equal to negative 1.22. That would be the same probability. But then instead of using table C1, I've got to use table C2. And negatives are first in this picture. So I go to negative 1.22, negative 1.201, 1.22 is 1112. Now I go to 2.15. But that means I have to go all the way through the negatives to the positives on the next page. Please separate pages. Thank you. 2.1, 0, 1, 2, 3, 4, 5 is 9842. And notice that if I subtract those, I get the same answer. That's lots of different access ways to get to the same answer, regardless of what piece I use. If I want to use my technology, I don't have to do all of this. I just have to put in the right lower limit and upper limit. Yes? I can do this in Excel. The command in Excel is normal.dist. NORM, and there it is right at the top, norm.distribution. Now notice when I start typing, it gives me information underneath that about what the rest of the command should be. And it includes value, mean, standard deviation, and then a flag for whether I'm using the CDF or the PDF. But it only gives me one number at a time. So if I want to give it 2.15 with a mean of 0 and a standard deviation of 1, and I'm using the cumulative 1. Oh, wait, they just said true. True for the cumulative. There's that 0.9842. So Excel only gives me one value at a time, whether it's from the CDF or the PDF. I'm almost always going to use the CDF. Whether I use it to do this like subtraction or I use the version where I'm starting in the middle, that's up to you. But that's only one value. The PDF really doesn't give me useful information here because that's only saying, well, that's the chance of getting this exact one number. It's not helpful. Questions so far? So if I want to finish this problem, I have to subtract the other one, right? Equals norm dot dist negative 1.22 comma 0 comma 1 because I'm using the standard normal, right? True for the CDF. And then I subtract those two to get the 8730. Well, it's rounded to 30 because there it's rounded to 298. It's going to round to 30. By the way, equals norm. If I don't want to keep typing mean and standard deviation, there's another distribution there with a dot S on it. That automatically does standard. Norm dot S dot dist. Then all I need to give it is the X value. 2.15, comma true. Same value, different command to get there. Make sense? Lots of different ways to access the same information. But I need to know how to use it. Well, somebody looked like you had a question on it?
Yes, I don't understand the difference between C1 and C2.
Okay, so the difference is the way in which we look at the left edge of our information. In C1, we're taking the values and starting at 0. Always. That's why that picture is in the upper left corner there, upper right corner. So I know I'm going to start in the middle and measure only to the right. Table C2 always starts as far to the left as you can go and measures to whatever number you want. This is truly the cumulative distribution function, table C2. This is a modified cumulative distribution. Think about the left half of that picture. This piece right here. What's the area in that whole white piece over there on the left?
0.5.
So I can get these numbers by adding 0.5 to the numbers on the left here. So that's with all of these numbers, you'll notice the difference is exactly 0.5 between C1 and C2 for the positive ones. But these, they've done the arithmetic for me already. It is totally up to you which one you use. I was trained with this one. So this is, well, actually, I was trained with a variation of this one. I was actually trained with knowing the tail, not knowing the middle. But you get to use whichever one you like or one of your technology pieces. But I'm all in favor of saying the first thing you should do, draw the picture. Because if I draw the picture, even if I don't know what the question is about, I know what I'm trying to find. Like, I just had this picture here. I've got 1.96. This is going to be the value in table C2. But because of symmetry, if I was given negative 1.96, I could subtract, because put together, those give me 1, right? But I could also say, well, maybe I want the stuff between 1.96 and negative 1.96. So I take this picture and I subtract this one away. That's why that's been whited out there. Wait a minute. That's 95%. This is a normal distribution. There were a couple of numbers that I was already given about normal distributions. we had a rule. Back when I mentioned Chebyshev, remember Chebyshev? Told me for any population how the stuff was distributed. And I said, but if it happens to be normal, we have a special case. And then there was for 1 and 2 and 3 standard deviations, right? I think it's 99.7. Maybe not.
9973.
73. I knew there was another number there. I couldn't remember what it was. Now that actually gives me 2 other really useful pieces of information about the normal distribution. It means if I look at my crappy picture, and I'm going to cheat, and I'm going to take the book's better picture instead of my crappy picture. Ready? 1 standard deviation is right there. That's z equals 1, isn't it? 0.2, 1.6. There's z equals 1, that line. Yes? And over on the other side, here's z equals -1. This area is 0.6826, which means that area is half of it, 0.3413. If I move out to 2 standard deviations, that's 0.9544. If I move out to 3 standard deviations, that's our 0.9973, which means outside of 3 standard deviations, that's a very, very tiny amount of area, isn't it? But I can do all of that directly from here, as well as verifying those values out of my table. That's useful. Question. Assuming, as I did before, heights are normally distributed. What height would you say is the top 1% of all adult American males?
Yeah, maybe over 7 feet.
But why 7? Why 7 feet? Let me see if I can make this exact. Remember, we said that for height, the mean was 70 and the standard deviation was 2 inches. And now I want to know what height is the top 1%. Wait a minute, percent, that's asking about a probability. If the chance somebody is really, really tall is only 1%, then I'd want to know where the drawing line is, right? But let's think about our normal distribution again. What I'm really asking you to do is to figure out where this area is 0.01. Where's the cutoff for 0.01? This is a little harder. I need to work backwards out of my formula. I want the area to be 0.01. Or either table C2 or table C1. Alessandro, which one do you want to use? That means I want the rest of this to be 0.99, right? So now I go to my table and I start looking for 0.99. I know I'm going to end up with a positive Z value, right? Because I'm over here on the right-hand side. So I'm going to look on the positive C chart and I start looking for bigger and bigger numbers, 0.99, 0.97, 0.98. Here we go, 0.9901. There's my number. 2.33. So that cutoff line is where Z is 2.33. If I want to be more precise, it should be between 2.32 and 2.33 because the number was 0.9901, right? I can approximate between those two. I can use a linear interpolation if you want. I'm not going to bother with that. See, I couldn't get directly to an X value from that. What height is this? This is the Z value. What height is this person? I know a Z. How do I get the X?
The formula.
Exactly. I'm going to use that formula backwards. I have Z equals X minus mu over sigma. I'll put in all the numbers I know. 2.33 is X minus 70 over 2. And now I know exactly how tall this person needs to be. 4.66 equals X minus 70. So X equals 74.66 inches, which is only 6'2" and change. If heights are normally distributed with a standard deviation of 2, then anyone over 6'3" is in the top 1% of people. Maybe I'm wrong on the standard deviation. Maybe the standard deviation is bigger. But the last time I looked at this when I made notes, the standard deviation was only 2. Means some people are really exceptionally tall. I could go to the top 0.1%, right? I could also say, oh, the top 10% of people in a certain normally distributed population, or the middle 20%, interquartile range. Interquartile range was the middle 50. What if I wanted the middle 50%? Then I need 25% up here and 25% down there. I need to find on table C, I need to find where 0.25 was for an area. I need to find where 0.75 was for an area. And that would give me the cutoffs. So I can draw these lines on my curve and then figure out what probability I'm going to want to get. On page 245, table 3.7 actually gives me the correct number. I said 2.33. They give 2.326 for 0.01 in the right tail, or 98% if I'm looking for the middle, 1% at the bottom, 1% at the top. So depending on which situation we're looking for, these values may be useful and worthwhile. These are a lot of benchmarking values in different pieces of our industry standards. I want the top 20%, I want the top 5%, whatever it is, I'm going to get them out of this, assuming my population is normally distributed. I'm working my formula backwards, right? That's how I got the X value from the Z. That's how I got the Z from the area. If I want to go backwards, I'll need to go backwards in my technology too. Under my distributions, there's an inverse normal. Option number 3 here. I want the area to be 99%, right? 0.99. There's my Z-score. I want to do an inverse normal here. Equals NOR. And look, there it is. There's a normal inverse and a normal S inverse. So I can do the standard inverse right there. Norm.S.inv parentheses 0.99. Same number. I love having the technology to do this. I like not having to depend on it. And that's the reason I give you these tables. You will be provided them during exams, the exact ones out of the back of the book. If you know how to do that on the calculator, you're welcome to do so. You just need to tell me that you did it on the calculator on the exam. Write down this command. This is what I did. I'll know what you did. But I can use these tables in both directions. I can start with any normal distribution, standardize it, and then either find probabilities from it or use probable areas to find cutoff values in either direction. Questions? There's a lot of why and wherefore here. Why would I bother doing this at all? I promise there's a really good reason. And it's coming up. But it will be coming up on Monday. I will see you all then. Have a wonderful rest of your day. I'm happy